Okay. So these were the kind of problems that we worked last time, where if you had an integral of sine times cosine with both of them raised to integer powers, if either one of the powers on sine or cosine were odd, specifically, if they were odd, you could break off one of those functions, or one of those factors, use the Pythagorean identity to rewrite the remaining factors in terms of the other function, and then use a substitution that would allow you to finish the problem. But the problems that we looked at only dealt with sine times cosine. What we're going to look at today is how do you handle products of tangent and secant, and how do you handle products of cotangent with cosecant. Now, I'm not going to explicitly write the rules for both cases on the board, because if you look at, let me turn the pencil around, but if I write, I don't want to keep these up here, but at least I want you to see them. So here are my identities. Sine squared of x plus cosine squared of x is equal to 1. We have tangent squared of x plus 1 is equal to secant squared. And we have cotangent squared of x plus 1 is equal to cosecant squared of x. What I want to point out to you is notice that the identities for tangent and secant is almost identical to the one for cotangent and cosecant. You just replace tangent with cotangent, and you replace secant with cosecant, and now you have the other identity. That's going to be true in the strategy that we write down for how to handle products of tangent and secant together. If you have a product of cotangent with cosecant, you would just follow the same exact strategy. It's just wherever you see tangent, you're going to put cotangent in its place. And wherever you see secant, you're going to put cosecant in its place. Notice that the identity for sine and cosine is different. You had to add the two squared functions together to get one. This is the one that's different from the other two. So that's why you'll see that the strategy for handling this case was looking for odd powers. Whereas over here, it's going to change a little bit. In one case, you're going to be looking for odd, in one case, you're going to be looking for even. But for the product of tangent and secant and the product of cotangent and cosecant are the same strategy. So let's get rid of this. And by the way, it might be a good idea to print out the unit circle, print out the identity sheet, and just start bringing it, just keep it in your notebook, bring it to class with you. Because there may be values from the unit circle that we need in a problem, and I'm just going to write it on the board. And if you've got the unit circle, you can just pull it from that. I know if you've had Mr. Escaday, especially if you had him for trig, that you're probably used to having to memorize these, but we have enough calculus to worry about that I want you to focus your cognitive burden on dealing with the calculus part of it, not memorizing trig functions. Okay, so the last case for sine and cosine was in the event that both the powers of sine and cosine were even, breaking off one of those factors wasn't going to assist you. You had to use half-angle identities in order to bring that power down. So for the case, well, we did a couple of these, maybe not these very problems, but this is what I want to get to, the strategy for handling products of tangent and times secant. Okay, so the key identity we're going to be using to simplify this is the 1 plus tangent squared equals secant squared. Now these integrals that are right here, you should learn these integrals and just add those. Like if I were to tell you that the derivative of sine is cosine, or that the derivative or the antiderivative of secant squared is tangent, I'm not applying a formula. I'm using my differentiation rules. So this is those two integrals. You do not need to evaluate those on a test. If you ever encounter integral of tangent or integral of secant, you can substitute their respective expressions in there. Now it has to be absolute value here because we don't know what the limits of integration are right here. We need these limits. We need the natural log to be defined. Remember, natural log is not defined for negative numbers, and it is possible for secant to be negative. But if we take the absolute value of it, then we're guaranteed that that expression is going to be positive and that the natural log is defined. Outside of class, sometime soon, take this function, take both of these functions, and take their derivatives and see what you get. And see if you don't get tangent for the first one and secant for the second. It looks like you might not, but actually take its derivative. Use your differentiation rules and see what results. It's going to simplify to tangent. The second one will simplify to secant. See if you can't figure out how, well, not necessarily figure out, but verify that those are true. And if you can do that from this point on, you can just substitute those integrals whenever you see them. Okay, so we're going to start this case much the same that we did for sine times cosine. So notice that in this problem, that in this expression, m is the power of tangent, n is the power of secant. The first thing we're going to check is the power of secant even? If it is, we're going to take two factors of secant and break it off. Why are we taking two factors of secant? Because what is the derivative of tangent? It's secant squared, isn't it? We're breaking off two factors so that this secant squared together with this dx, that will be your du after you do a substitution. So you need to keep two factors of secant off to the side, and then all of the remaining factors of secant we're going to replace with using this expression that secant squared is 1 plus tangent squared. And that will express the remaining factors of secant in terms of tangent. So starting with this expression, notice that I said if n is even. That means that this power of secant is 2 times some number. Not 2k plus 1. That was when we were dealing with odd numbers last week. But if it's even, it's just 2 times the integer. So if we look at this expression right here, we've got secant to the 2k power. That is the same as taking, well, something's missing. Okay, before I write it in, I'm going to ask y'all. Look right here. I've taken off, this is the two factors of secant that we were going to break off. This is going to be my du right here. I want to take the remaining factors of secant. Notice that it's k minus 1 now. Because if I take two factors away, this goes to 2k minus 2, right? Factor the 2 out. So it's 2k minus 1. And that's the same as taking secant squared raised to the k minus 1 power. Now this should be, I just noticed this, and I'm going to add it in right now. This is secant squared of x. I have to take the secant of something. And I guess I forgot it right there. But what we're using right there is the fact that if I say something like this, x to the 2 times 5. This is x to the 10th right here. I can write this as x squared raised to the 5th power, because that's the rule of exponents that's governing this. If you have an exponent that is a product, you can write this as a power of a power, which is exactly what we did. Only I wanted the 2 on the inside and k minus 1 on the outside. The reason we want it in this order is because we're about to use this substitution right there. And this secant squared of x is going to get a substitution. The other secant squared, nothing is going to happen to it right now. But if you look at all of this, everything here is written in terms of tangent. So if we let u equal tangent of x, this is going to be u to the ilm times 1 plus u squared to the k minus 1. All of this right here is du. So now it's a polynomial in u again. That's exactly what we were doing last week. By breaking these factors off in just the right way and using the trig identities, we can make a substitution that will turn a product of trigonometric functions into a polynomial function, which is a piece of cake to integrate. You just raise the power by 1, divide by a new power on each individual term. The trick is getting it into polynomial form. So for tangent times secant, if the power of secant is even, break off 2 factors of secant, write the remaining factors in terms of tangent, let u equal tangent. Okay, let's see, can I just... Okay, let's just come over here. I'm skipping ahead a little bit because rather than throw the entire strategy at you, we're going to do one piece of it and work a problem. So let me just... There we go. Where can I move it? Over here. There we go. At least now it's in order. Okay, I have an even power of secant. Now, I don't have a tangent here, but that doesn't matter. If I have an even factor of secant, then I'm going to write this, as secant to the 4th of x times secant squared. So break off 2 factors of secant. These 2 factors together with the dx, that's going to be your du after your substitution. Keep those. All of the other factors of secant, we're going to write in terms of tangent. So this is secant squared of x squared times secant squared of x dx use your trig identity to rewrite secant in terms of tangent. So now we have 1 plus tangent squared of x squared secant squared of x dx. Okay? At this point, now we're ready for our substitution. Integration by parts is not needed here. It's a substitution problem. And you let substitution be the function you just used the identity to convert to. not the one you converted from. So I'm going to let u equal tangent. du is going to be secant squared. And this is going to become the integral of 1 plus u squared du. And this is just a polynomial in u now. I need to multiply that polynomial out, sure. 1 plus u squared is 1 plus 2u squared plus u to the 4th du. You'll need to multiply it by itself and use FOIL there and collect your like terms. But that's what you'll get. Now that it is a polynomial written out as such, term by term, integrate by raising power by 1, divide by the new power. So looking at this integral right here, what is its antiderivative? Oh, really? So I'm going to go from this. It doesn't matter what order you do it in. Or if polynomials are usually written from the largest power down, but it doesn't matter the order. But with the order I have it written, it's u plus 2/3 u cubed plus c. And I'm done, right?
No.
Good. If you stop here, expect to rightfully get taken off of this. Because this is the answer to this problem, not the one we started with. Just substitute back what you stood for. So your answer is actually tangent of x plus 2/3 tangent cubed of x plus 1/5 tangent to the 5th of x plus c. Yes. I know I sort of crammed it down here at the bottom, but I was running out of room. But that's how you handle. Now this, if there would have been like a tangent squared in the problem, like if there would have been a tangent squared all the way back up here, the only thing that would do is it would, you would have a tangent squared to distribute after you multiply this out, and these powers would go up by 2. You would have u squared plus 2u to the 4th plus u to the 6th. But that's the procedure for doing it. So if the power of secant was even, that is how we broke off 2 factors of secant, and then we transformed everything else in terms of tangent. Now, if the power of tangent is odd, not even, if it's odd, what we're going to do is we're going to pull a factor of secant of x, tangent of x, off to the side and convert everything else in terms, convert the remaining factors of tangent into secant, and then your substitution would be u equals secant of x. Okay, so same sort of idea. Now, there really should have been, an n right here. Now it's right. Because secant still can have a power on it. Yeah, it looks like I'm going to have to fix this line because this should be an n. This should now be there should be a secant n minus 1 over here now. This will be better. So secant n minus 1 of x. We took one factor of secant and one factor of tangent. So that's why the powers of tangent and secant both dropped by 1. Okay, so now that we have broken off secant x tangent of x, this portion right here, that is the derivative of secant of x. We're going to save that for our substitution. What I want to do is rewrite the rest of these tangents in terms of secant. So everything here will be in, I'll be able to make a substitution with u equal to secant of x. So I would get what? This is secant squared of x minus 1 to the k times secant of n minus 1 x times secant of x tangent of x dx. Now I would still need to multiply out secant squared of x minus 1 to the k. And provided that k is small, yes, it's tedious to multiply it out using FOIL. There are shortcuts for that, like it would be useful if there was a class that we taught at LSUE where you encountered what's called the binomial theorem that would help us multiply out something like that very quickly. But unfortunately, we don't, and I don't expect any of my students to have encountered the binomial theorem or what's called Pascal's triangle. Both of those would allow it. Okay, a couple of y'all shook your head. You're familiar with Pascal's triangle. Pascal's triangle can be used to multiply out something like that very quickly. But I don't really have a whole lot of time to teach shortcuts that are not applicable to, that are not directly calculus problems. But here, once you get to this step, now let u be secant of x, then you can take its derivative. Its derivative will be secant of x tangent of x dx. And from that point on, it'll be a polynomial in u now. And you'll need to multiply it out, but you should be able to finish it. And I'm going to rewrite this because I had to correct it. I'm going to rewrite this and this. Okay. Now you might be saying, there's no secant here. That's okay. So right now, I see that I have an odd power of tangent. This is the same as if I did this. Oops. Do you agree? So far, so good. Okay. What about this? Any number, any non-zero value to the 0 power is equal to 1. I still haven't changed it. So I am going to break off a factor of secant of x tangent of x. Now you might be saying, but there are no powers of secant here to give. But what if I did this? Tangent squared of x times secant to the negative 1 x times secant of x tangent of x dx. What happens when I multiply secant to the negative 1 by secant of x? Add the powers together. You get secant to the 0, which is 1 again. So even though I had no factors of secant, I could write it like this. And this is now just going to be my remaining factors of secant. But this part of it is going to be my du in my problem. So now I'm going to rewrite the tangent in terms of secant Now, if I wanted to, I could use substitution right here and let u be secant of x. So du is secant x tangent x dx. So what am I going to have? I'm going to have the integral of u squared minus 1 times u to the negative 1 times du. Oops. And I'm not even going to try to attempt to cram it in here. Let's just start another page. Okay, now in this problem, I don't have a power out here that I got to FOIL out the u squared minus 1. I can just go ahead and distribute this u minus 1 indirectly. So this is equal to the integral of u minus u to the negative 1 du. This is u minus 1 over u du. Integrate this term by term. What is the antiderivative of u? 1/2 u squared. Yes. What is the antiderivative of 1 over u? Be careful. You know this.
1 over u times the natural log of u.
No. Think of what function has its derivative being 1 over u? ln of the absolute value of u. ln of u was the right idea. But because this is an indefinite integral and we don't know what u is, we have to ensure that we're taking the natural log of a positive number. So this is natural log of the absolute value of u plus whatever constant you have. And now just substitute back in what u stood for. So the answer to this problem is 1/2 secant squared of x minus the natural log of the absolute value of the secant of x plus your constant. That's it. Any questions? Now, the strategy we just talked about, go back and everywhere you see tangent, put cotangent. Everywhere you see secant, put cosecant. And that is the same rule that applies for the product of those cases. So because it would just be me repeating myself again for the next quarter of an hour, I'm not going to write those down separately. They're in the book if you want to see them. But there's a couple of cases I left off. What happens if the power of secant is odd, but the power of tangent is even? Now, neither of these rules for tangent times secant work. In that case, it's much more difficult than the sine times cosine case. We don't necessarily have half-angle identities, well, not explicitly, for tangent and secant. So all I'm going to say is you're not going to see those right now. We could probably do them with approximate integration, and we'll see that later when we get to like section 7.9, but that's a long way down the road. But for the types of skill we want to develop in this section, if you had that other case where the power of secant was odd, but the power of tangent was even, it's going to require a different integration technique than what this was going to do. So it's going to just be a case we're not going to deal with. The same thing for the cosecant, cotangent case where cotangent has a power that's even and secant has a power that's odd. Okay, let me see I know what's coming up. I just want to see where I'm at now that I had to move some slides around. I'm going to have to rewrite a couple of them. But what I want to remind you of that all of our answers at the end can be checked by differentiation. And in fact, the differentiation process usually takes fewer steps than the integration process did. So get in the habit of just checking your answer very quickly to make sure you're right. And I would highly encourage that, especially if you were working a test and I give you an hour to do it, and you finish it in 40 minutes and you have time left over, you lose nothing by checking your answers to see if they're right. Oops. Okay, so I at least want to talk about the motivation for what we're about to do in section 7.3, and then we're going to really get our hands dirty with it starting tomorrow. So, you recognize that equation from college algebra? You probably saw it as x squared plus y squared equals r squared. Or it may have looked like this. You have x minus h squared plus y minus k squared equals r squared. But if your center is at the origin, then h and k are 0, so you get x squared plus y squared. And I am calling the radius a instead of r. So it is this equation reduced down to this specific case. Here's what I want to do. I want to know the area of that circle. Do you remember your geometry and how you find areas of circles? It's okay if you don't. Pi r squared. That's your formula for area of the circle. But you don't get the area. You don't get to use the area formula. We want to find it some other way. We want to do it using integration, because integration is the area under a curve. So look what I do. I'm going to take this equation right here, and I'm going to solve it for y. So I'm going to get y by itself. In other words, just take the x squared and move it over. So I subtract it from both sides. And now if you want to get rid of this squared, you can take the square root of both sides, but you've got the plus or minus. Now, this is really two functions right here. The positive square root of a squared minus x squared is the top semicircle of the graph. The negative square root of a squared minus x squared is the bottom semicircle of this graph. But those two together encompass the entire circle itself. and I want to know what the area inside is. But I don't want to find the area of the whole thing. Do you agree that if I only find the area of that shaded region and multiply it by 4, I get the area of the whole thing? It's centered at the origin. So the origin and the axes are going to split that circle up into 4 equal pieces. So if I just find the area of one quadrant, I'll have found the area of the circle. Okay, I can do that by looking at this piece of the graph. That is the positive square root of a squared minus x squared, and I would be integrating from 0 to a. That would be my integral. There it is. So the area of the circle is 4 times the area of this top semicircle integrated between 0 and a. Now, a is a constant. That's all it is. But try integration by parts. It's not going to work. If you try substitution, substitution, if you let u equal x squared, you could try that. But if u is equal to x squared, look what du is equal to. There's no x anywhere here to pair with this dx. So substitution with u equal to x squared isn't going to work. Integration by parts really isn't going to work, because for integration by parts, you need to be able to split u dv completely apart from each other so that their product is the original function. Well, the only product I have right here is between the square root and the dx itself. You would need to let u be this entire radical, and du would just have to be dx, and you're not really going to make any progress there. So integration by parts isn't going to work. And this is clearly not a function of the form sine to a power times cosine to a power. We need something else. So this is the kind of problem that we're going to tackle tomorrow. No way I can start that now because we're at the end of class. So let's say that I picked this this worksheet up on Thursday, okay? So there will be another worksheet going up in the next couple of days. It's going to cover the material we're doing this week. So ordinarily, I wouldn't give a week and a half to work on worksheets, but I'm being a little forgiving at the beginning because I want everybody to get back into thinking about calculus, and just the more you work on it, the more you'll stir things back up to the surface, and you'll have a little bit quicker grasp on some of these problems. If you have questions about that worksheet, my office is right downstairs. Come talk to me about it. And if you've got a problem that's incorrect, I'll tell you. And I will probably ask you some questions that will lead you toward the right answer. But apart from that, we are done for today.